Okay, so today is the last lecture of part 1. So there will be 2 classes of recitation today. So because this is the end of the part 1, and starting from the next week, we will start a new topic on martingales. Okay, so today's goal. First, we recall of 2 standard results about finite state space, so existence and the uniqueness of stationary distribution and the convergence theorem. And today we will generalize this result to countable state space. But for the countable state space, we have 2 different notions compared to the finite state space case. These 2 notions is we have recurrent and positive recurrent. Then we can introduce what is the stationary distribution and what is the convergence theorem. So first, a quick recall of what we have for finite state space. So for finite state space, we have proved that almost surely the return time is always finite. And we also proved that the expectation of a return time is always finite. So this is what we proved in the first lecture. And from there, we show that there always exists a stationary measure. The definition of the stationary measure can be given explicitly. So we fix a vertex x, then this stationary distribution is the expectation of number of visits to a state y before the first return time. And then normalized by the total mass of this measure. Because the expectation of first return time is finite, so this measure is well defined, and we also check that this is a stationary measure and it has total mass 1. So this is a stationary distribution. And then we prove that the marginal law of the Markov chain will converge to the stationary distribution under total variation distance. And we also show that the decay, the total variation distance between these 2 measures goes to 0, and it decay like a power law in n. So this is what happens for the finite state space. First, for the countable state space, the first item doesn't work always. So first, let's introduce recurrent and transient. Because this first item is not always true in the countable state space. In the last lecture, we have already shown that if the Markov chain is irreducible, then one state is recurrent. So it means that the first return time is finite almost surely, then all states are recurrent. So this property classifies the irreducible Markov chain into 2 different classes. The first one is called recurrent, the second one is called transient. And in the last lecture, we also proved that simple random walk on Z2 is recurrent, but the simple random walk on Z3 is transient. Okay, so this is the first difference. The probability for the return time to be finite is not always to be 1 in the countable state space, and this gives us 2 classes of Markov chains, recurrent or transient. The second difference is this item is not always true, even suppose the first item is true. So even in the recurrent case, we don't always have finite expectation. So this is the second difference. And we are interested in this property is that because we want to define stationary distribution. And in this finite state space case, we see that this is our construction of stationary distribution. So if we can show that this guy is still finite, then we can construct the stationary measure in the same way. So this is why we are interested in why the expectation of first return time is finite. But after we study the countable state space, we find that this is not always true. So this gives us further 2 subclasses of Markov chain. So now for countable state space Markov chain, we know that there are 2 different types. according to whether the probability of first return time is finite is 1 or not. So transient or recurrent. And then we study whether the expectation of first return time is finite. And this gives us two further subclass of Markov chain. So 2.1 is positive recurrent. For positive recurrent, I mean that the expectation of first return time is finite. Or non-recurrent. And this means the expectation of return time is infinite. Okay, so this is the different type of Markov chain. So in order to well define what is positive recurrent, we need a lemma. So this lemma says if one state is positive recurrent, then every state is positive recurrent. So the lemma says if the following two conditions are equivalent. So one state is positively recurrent. Or the expectation of first return time is always finite for any y and x and y. Okay, so after we prove this lemma, we know that if one state is positively recurrent, then all states are positively recurrent. So this gives us two types of different Markov chain, positive recurrent or non-recurrent, and there's no difference for different states. Okay, so prove this lemma. So if you still remember how we proved that one state is recurrent, then all state is recurrent, then the strategy of the proof is very similar. So we show that 1 implies 2. So suppose for some vertex it is positively recurrent. Then we want to show that for any x and y, the expectation of first return time is always finite. And the proof has 3 steps. We first replace starting point by x. And then replace this part by y. And finally, replace both of them. So this is the 3 steps of the proof. So first, how to compare the expectation starting from x and the first hitting time of x0. And the only thing we know is the starting from x0 and the first return time of x0 is finite. So we need to compare this expectation to this one. So this is the expectation of the first return time, and we know that if we put an indicator function, it will decrease this expectation. So suppose tau x happens before the first return time. Of course, it's only decreased the expectation. Okay, so now suppose we know that tau x happens before the first return time. Then this Markov chain, up to what happens at this time, we know that after this time, it is a new Markov chain starting from x. Okay, so this is greater than So now I just subtract this stopping time by another time. So of course the expectation is also decreasing. And now for this expectation, let us see. We know that we first hit x before going back to x0. And then at this time, we know that this is just a new Markov chain starting from x. And this part of the time is just the time that we start from x and before we hit x0 again. So what we have from Markov property, we know that this expectation equals the probability that after we first hit x, we're never going back to x0. And after we arrive at x, we know that this future part is just a new Markov chain starting from x, and we are calculating the expectation of tau x0. And this is exactly the quantity we want. And we know that this part is finite. So in order to say this expectation is finite, we only need to check that this probability is strictly positive. So this is the probability that we have a Markov chain starting from x0, and we hit x before going back to x0. So by irreducibility, we know that this probability is strictly positive. So now we have some finite quantity bounded this strictly positive thing times another expectation. So this implies that this expectation is finite. Okay, so this completes the proof of the first step. Okay, second. For the second step, we want to calculate the expectation of starting from x0 and the first hitting time of y. So, and the only thing we know is the expectation of first return time going to x0 is finite. And we need to compare this time to this time. But of course, tau y happens either before it or after it. If it's before it, then of course it can be bounded by this guy, and then the expectation is finite. But what happens if tau y happens after this time? So now we have to divide the time length according to the return time to x0 and see where is tau y. So we define a sequence of hitting time of x0. So this tau 0 starts from 0, tau 1 is the first return time, and tau k plus 1 is the time after tau k that we're going back to x0. So this sequence of time tau k just divide the time according to different intervals. And now we want to see where this tau y located, so which interval it is in. And we divide the expectation according to this different event. So suppose tau y is between tau k and tau k plus 1. Then we can bound this tau y by tau k plus 1. Okay, so for this indicator function, it says that tau y between tau k and tau k plus 1. And we know that this indicator function can be written as the difference of 2. So this indicator function equals tau y greater than tau k minus tau 1 is greater than tau k plus 1. and we split the two parts, what we have is okay, so look at the second term. The second term is we summing over k starting from 0 and from k plus 1. But for tau k plus 1, and here is tau k plus 1. So now we just change the index by from k to k plus 1. So now it's just a k from 1. Okay, then we see that we can compare these two quantities. So when k equals 0, so we can also write the second summation starting from 0, because when k equals 0, tau 0 is 0, so the expectation is 0. And then we can put these two summations together, then it will become okay. So in fact, I've done nothing, just re-index the expectation here, and then we get this one. Okay, so here, let us check what's this expectation. It tells us at tau k, so from time 0 to tau k, we know that we never hit y. And at tau k, we know that we're just a new Markov chain starting from x0. And this time is the time difference that at tau k and to the next time that we're going back to x0. So now we divide this Markov chain according to what happens before tau k or after tau k. Then we just have this expectation equals the probability of what happens before tau k. And then the expectation of what happens after tau k is just a new Markov chain starting from x0. And we already know that this part is finite because tau 1 is just first return time of x0. And we only need to check what's the probability of this part. So what is the probability of px0 tau I greater than tau k? So it starts from tau I greater than tau 1. And we denote this probability as q. By irreducibility, we know that this probability is strictly less than 1. And then let us check what's the probability that tau 1 is greater than tau k plus 1, knowing that tau 1 is greater than tau k. So if we know that tau 1 is greater than tau k, so it's just from time 0 to tau k, we never hit y. And after tau k, well, just a new Markov chain starting from x0. And this probability is just say, before we're going back to x0, we don't hit y. So this is exactly the same as q. So this implies that by proof by induction, we can show that the probability of tau I greater than tau k is q to the power k. So then we go back to the summation here. So this is bounded by q to the power k times the expectation. And since q is strictly less than 1, we know that this is finite. Okay, this is the second step. And finally, we can complete the proof by changing both starting point and target point by other points. So for starts from x, and the expectation of first return term of y, yes?
Sorry, how do we know that those two sums are finite?
Because q is strictly less than 1, so this part is finite.
The one on the fourth line.
Fourth line.
We break it into two sums.
So here, yes. This question is correct. So in fact, before we move everything aside, we have to show that the two summations is already finite. But to this part, you can use either Fato's lemma or because all of the quantities are finite. So in fact, you can operate by just a cut to a finite time and then take the limit. Yeah, this is a good question. So in fact, from here to here, we need to check that these two terms are finite.
So we're finite even if it's non-recurrent?
What?
We're finite even if it's non-recurrent?
Even if it is what?
If it's not positive recurrent, but like non-recurrent.
Wait. I think the precise argument is we have to cut these two summations up to some finite time, and then operate and then show that the tail term goes to 0, something like this. Yes. Okay. Yes, this is a good question. So in fact, you need to check why we are allowed to go from here to here. Okay, so final step, starting from some x, and we want to calculate what's the first return time of some other state y. So for this step, the idea is similar as how we prove the recurrent of the Markov chain. So suppose we start from x. We know that this first return time to y is bounded by tau x0 plus tau x0 y. So this is the first time we go to x0. And this is the time that after we go to x0, we hit y. So of course, this tau y plus is bounded by summation of these two. And for the second expectation, we see that so this is just, we know that after we hit x0, this is just a new Markov chain starting from x0. And this tau x0 y is just how long is the time that the Markov chain hit y after x0. So this is exactly starting from x0, the expectation of tau y. And from the first step and the second step, we know that these two quantities are both finite. So the summation of the two is also finite. Okay, so in this lemma, we show that if one state is positive finite, positive recurrent, then all states are positive recurrent. So now we have complete the classification of Markov chain. So first, we need to check the probability that whether the return time is finite. This gives us two classes of Markov chain, two classes. One is called recurrent, and another one is called transient. So in the class of recurrent, we continue study whether the expectation is finite. And this gives us two further classes. One is called positive recurrent or non-recurrent. So non-recurrent is the expectation is infinite. And then we can see what's the relation between positive recurrence and the stationary distribution. So just in the same way as finite state space, we see that if the expectation of first return time is finite, we can construct a stationary measure. And in the countable state space, the argument is similar, and even we can prove a stronger conclusion. So for an irreducible Markov chain, so it is positive recurrent if and only if there exists a stationary distribution. Okay, an irreducible Markov chain is positive recurrent if and only if there exists a stationary distribution. Okay, so first we show that positive recurrence implies the existence of stationary distribution. So in fact, the proof of this part is exactly the same as the finite state space. So we first fix some x, and we define a measure we define a measure pi theta, so it calculates the expectation of the visits to y before going back to x, and we can check that this pi theta is a stationary. So the proof exactly the same as the finite state space case, and then we check that the total mass of pi theta is the expectation of the first return time. And since we assume that we are in the positive recurrent case, we know that this expectation is the total mass is finite. Since it is finite, then we can define a normalized measure. So pi theta normalized by its total mass. And then this pi gives us a stationary distribution. So the proof is exactly the same as the finite state space case. Okay, so the difficult part is how to show that if we have a stationary distribution, then we must be in positive recurrent case. Because in the finite state space, we don't have such a problem. In the finite state space, we know that we are always in the positive recurrent case. So there's no such question. But in the countable state space, the conclusion is if we have a stationary distribution, then we must be in the positive recurrent case. And the proof for this argument have 4 steps. First, we will show that, okay, suppose pi is a stationary distribution. First, we will show that pi is strictly positive at every state. And then we show that the Markov chain X is recurrent. So of course, before we show it is positive recurrent, we have to first show it is recurrent. If it is not recurrent, then there's no hope for positive recurrence. Okay, third step, we will show that the time reversal of this Markov chain is recurrent. And finally, we show that this chain is positive recurrent. So finally, in fact, precisely what we show is pi x times the expectation of the first return time equals 1. So this is what we proved in the last step. So here we say that after we complete the proof of 4, because we know that pi x is always strictly positive, so this implies that the expectation here has to be finite. So this shows that we are in the Markov chain is positive recurrent. Okay, so first, why the stationary measure has to be strictly positive at every state. So suppose this is not true. So assume it is 0 for some states. And the only thing we know is pi is stationary. So since pi is stationary, we know that pi times p equals pi. So this implies that pi x0 equals pi y times p y x0 summing over all y. And so from here we see that if pi y x0 is strictly positive, because the left-hand side is 0, in the right-hand side, all the term is non-negative. If py x0 is strictly positive, then this guy has to be 0. And since the Markov chain is irreducible, we can find a chain starting from any vertex end up at x0 and show that it has to be 0 along this chain. So because this Markov chain is irreducible, for any vertex x, we can find a sequence of states. So there is a strictly positive chance to jump from one to the next. And this chain starts from z and at x0. So from the argument here, we say that x0, if pi x0 is 0, then the previous step is 0. And then the step before it has to also be 0. And finally, we can conclude that pi z is 0. So now pi is 0 everywhere, but we know that pi is a probability measure, so it has total mass 1. So this contradicts with the fact that this pi has total mass 1. So this is impossible. Okay, so this is the first step. Second, we will show that this Markov chain is at least recurrent. So to this end, we check what happens to the last visit of x. So consider the last visit. So we divide what happens according to when is the last visit of x. So suppose n is the last visit to x. So after time n, we never hit x again. And alpha n is the probability of this event. But here, just know that we're starting from stationary measure pi. Okay, so from on the one hand, we know that the probability alpha n here is we start from pi, we hit x at time n, and after x after n we never go back to x, because at n we know that after n is just a new Markov chain starting from x. So alpha n equals first the probability of what happens after time n. And then after time n, we know that we never go back to x. So it's just the x return time equals infinite. And since we start from stationary measure pi, we know that the marginal law of any time xn has the same law as the stationary measure. So the first part equals exactly pi x. Okay, so this is what happens. This is what we can derive from the Markov property of the Markov chain. On the other hand, because we see that all these events for different n, they are disjoint events. So this event are disjoint. For different n. Since they are disjoint, of course, the summation of all the probabilities is less than 1. Okay, so compare these two facts. One thing is this alpha of n in fact doesn't depend on n. And another part of the observation is the summation of for different n of alpha n is less than 1. So now what we have is we have an infinite times this quantity is less than 1. So this implies this quantity has to be 0. So combining these two parts, we know that pi x times this probability is 0. And from the first step, we know that pi x is always strictly positive. So this implies this probability is 0. So this shows that our Markov chain is recurrent. So the first return time is finite, has probability 1. So it is recurrent. Okay, recurrent. And then what about the time reversal of this Markov chain? So for the time reversal of this Markov chain yn, we know that it is just a Markov chain moving with transition matrix given by this guy. So this is the definition of time reversal of Markov chain. So it's just a Markov chain, but the transition matrix is given by p hat, defined in this way. And we can directly check that pi is also stationary for p hat. Since it is stationary for p hat, we repeat the same proof as 1 and 2. We can show that yn is also recurrent. So just to repeat the same proof in the step 1 and the step 2, we can show that the time reversal of this Markov chain is also recurrent. And then finally, let us check whether the expectation of first return time is finite. So what's the expectation of this first return time? So just to recall a standard effect, if a random variable big N takes value in non-negative integers, we know that the expectation also equals the probability of N is greater than smaller n and the semi over all n. So this is a standard effect for random variable take value in non-negative integers. And this tau x plus is a non-negative, is a random variable take value in non-negative integers. So we just split in this way. Okay, so this probability is we start from x. The first return time is after n, and now we divide this event according to what happens at n. So I just divide according to what happens at time n. So now what we do is we reverse this time Markov chain. So this probability, this part, it says that we have a Markov chain starting from x. At time n, we hit to y. And from time 0 to n, we know that we never hit x again. And now we reverse this Markov chain. We know that the time reversal of this guy has the same law as the Markov chain, moving with p hat. Okay, so here by p hat, it just means the Markov chain moving according to this transition matrix p hat. So I just reverse this Markov chain, and now this is a Markov chain starting from y, and at time n it hits x. And from 0 to n, we're just knowing that it never hit x. But here we can already see that tau x plus is the first time that the Markov chain hit x. And we know that at time n it hits x. So in fact, this event tells us tau x plus equals n. And now we sum it over n. So we switch the role of these two summations. In fact, we also need to precisely check why we are allowed to change the order of these two summations. So we first sum it over all n. So here what we do is just the probability of tau x plus equals n, and we sum it over all n. So this just tells us this is exactly the probability that tau x plus is finite. And since we just proved in the third step that the time reversal is recurrent, so we know that yn is recurrent. Since it is recurrent, we know that this probability equals 1. And finally, we just assume that this is stationary. This is pi is a stationary measure, is a stationary distribution, so it has total mass 1. So this proves that pi x times the expectation of first return time equals 1. And since pi x is strictly positive, the expectation of first return time is always finite. So this shows that we assume there exists a stationary distribution, then we must be in the positive recurrent case. So what we have is, in fact, in the countable state space case, stationary distribution is equivalent to, say, positive recurrent. So if they are just the two statements that they are equivalent. So as a corollary from the proof of this theorem, we already say that if a Markov chain is positive recurrent, then there exists a unique stationary distribution. And for this unique one, we know that at each vertex, it is strictly positive. And in fact, we also know that it equals exactly 1 over the expectation of the first return time. Okay, so this is about stationary distribution. And the final theorem of this part is about convergence theorem. Okay, so last one, convergence to the stationary distribution. This is the conclusion we're going to prove in this lecture. So the total variation distance between the marginal law of xn and the stationary distribution will converge to 0. So just a quick recall that in the finite state space case, in fact, we show that this it decays in an exponential fast way in n. But in the countable state space, we can't prove such a strong argument. If you still remember how we prove for the finite state space case, you can also tell that our proof highly based on the fact that we are in a finite state space case, and that proof doesn't work for the countable state space case. And in fact, in the countable state space case, we can only show that it will go to 0, but we can't give a good estimate on how fast it will converge to 0. So suppose Markov chain is irreducible and aperiodic. So this assumption is the same as in the finite state space case. And then the conclusion is the marginal law of xn will converge to the stationary distribution in total variation distance. Okay, so to prove this theorem, if you still remember that there is a characterization for total variation distance. It says that the total variation distance between two probability measures is always bounded by any coupling that, so the total variation distance between two probability measures is always bounded by the probability that x is distinct from y, and x and y is any coupling. Is any coupling of these two measures. And now we want to show that the total variation distance will go to 0. So the idea is we want to construct a coupling of two Markov chains. We want to construct a coupling of two Markov chains. And one of the Markov chain xn starts from x0 equals x. And another one starts from stationary measure. And we want to couple them so that at time n, they are very close. So this gives us an upper bound for the total variation distance between this Pn and the pi. So this is the idea. We want to construct a coupling between two Markov chains. One starts from x0 and one starts from stationary measure. And we want to show that as n goes to infinity, the total variation distance between these two. So the probability that they are distinct will go to 0. Okay, so this is the idea. So we want to construct a coupling of two Markov chains. So if we put these two Markov chains together, so in fact, we can view this process is a Markov chain, but the state space is omega times omega. So this is a process taking value on omega times omega. So in order to construct a coupling of this process, so in order to construct how this process moves, we need to introduce a transition matrix, but this transition matrix from omega times omega to omega times omega. Proof. So define Q is a transition matrix. So now we define the transition matrix Q. So it's jumping from one point in omega times omega to another point in omega times omega. So first we will show that this Q is a stochastic. So it is a good, well-defined transition matrix. And then we show that this Q is irreducible. And then we show that this Q is recurrent. And finally, we construct this coupling of two Markov chains. So here we see that after we complete the proof of the previous three steps, then this Q indeed gives us a good transition matrix on the state space of xn and yn. And now we can just define xn and yn as a new Markov chain, starting from measure of this one and jumping according to Q. And this new Markov chain, we know that it is recurrent. So since it is recurrent, we know that the heating time will decay to 0 as n goes to infinity. So this is the strategy. Okay, so first, why this Q is a stochastic matrix? So we say that this Q is a stochastic matrix. First, this Q is non-negative at all entry. So of course, because it is the product of two probabilities, this is non-negative for all points. And then we need to check that if we summing over second coordinate, then the total mass of this transition matrix is 1. So we need to check that this summation equals 1. So by definition, we know that it equals pxz times pyw. And now we are summing over z and summing over w. When we're summing over z, we know that the first part will give us 1 because p is a stochastic. And when we're summing over w, the second part will give us 1. So it's equals 1 times 1. And equals 1. So this shows that this Q is a well-defined transition matrix. Okay, second, we want to show that Q is irreducible. So to show Q is irreducible, it means that for any states there exists n such that Qn, so there is a strictly positive chance to jump from one state to another state in finite times. Okay, so we want to show this probability is strictly positive. And you can easily check that this probability equals p to the power n. And pn to the power p to the power n from jumping from y to w. So now we need to check that for any x, y, z, w, there is a big N such that both of them are strictly positive. So this is goal. So why this is true? If you remember what we proved in the first lecture, we showed that for the finite state space case, if the Markov chain is aperiodic, then there exists a universal constant n such that as long as smaller n is bigger than big N, then this probability is strictly positive for all states. But attention is that in that proof, we used the fact that the state space is finite. But now our state space is countable, so we can't apply that theorem directly. And we have to check what happens in the countable state space case. Okay, so first, what happens to the countable state space case? The idea is similar as before. First, we consider what's the odd integer number such that p and xx is strictly positive. And we can still check that this ax is closed under addition. And this ax has greatest common divisor equals 1 because we assume that it is aperiodic. And from combining these two facts, we know that this ax contains all but finitely many integers. So there exists an x such that p n x is strictly positive for any n large enough. So this part is still true, even if we are in the countable state space case. And since our Markov chain is irreducible, we know that there is a strictly positive chance to jumping from x to z. And now we define
I'm sorry.
yes.
Why does the x have a GCD close to 1?
Because we assume this is an aperiodic chain.
Oh, sorry.
Yes, I should first recall the definition. So just to quickly recall this. Aperiodic for countable state space cases is defined in the same way as finite state space. So it just says if this is ax, then the greatest common divisor is always 1 for all states x. So this is definition of aperiodic. Okay, so now we'll continue. We define big N equals smaller nx plus this r xz. And from the argument here and the argument here, so combining these two, we know that for any n greater than this big M, p and xz is strictly positive. So in fact, this is the only place that we use that the Markov chain is aperiodic. Okay, so now what we show is there exists an mxz such that so P and XZ is strictly positive as long as n is big enough. And of course, we can also define MYW in a similar way. Just switch the role from XZ to YW. So there is also a finite number MYW such that P and YW is strictly positive as long as n is big enough. And now we just only need to define this big N to be the max of the two. And then this shows that P and XZ is strictly positive, and P and YW is strictly positive. So define a new measure on omega times omega in this way. So you can also view it as a tensor product, or you just view it as just a notation. So I define this measure in this way, and we can check that this measure is stationary for Q. And we can also check the total mass of this measure equals 1, because the total mass is summing over all x. Summing over x, this gives 1. Summing over all y, this gives 1. So the total mass is 1 times 1 equals 1. So this new measure defined on omega times omega is the stationary distribution for Q. And by the previous theorem, we know that Q is a positive recurrent. So we not only prove it is recurrent, we also prove it is positive recurrent. But in the latter step, in fact, we only need the property that it is recurrent. Okay, so this is the third step. This big Q is positive recurrent. And finally, we can construct this coupling. So we construct the coupling of two Markov chains in the following way. So this Markov chain starts from a measure so it starts from the case that x0 equals x, and y0 is an independent random variable sampled according to the stationary measure. So this is the starting measure. And then after the starting measure, we move this Markov chain according to this transition matrix Q. So this is a Markov chain. And then we define a time. So here, Z0 is just some fixed vertex in the state space. So tau is the first time that this Markov chain hits a fixed vertex. And so we run this Markov chain up to time tau. And after time tau, we just put the two processes together and they never separate again. So I'm jumping and moves according to P. So in this way, we construct a coupling between two processes, xn and yn. So the joint law of these two processes is a Markov chain, and the transition matrix is big Q. And then let us check what's the total variation distance we want to study. So we know that this total variation distance is bounded by the probability that xn is distinct from yn, because we know that the marginal law of xn is Pn, and the marginal law of Yn is stationary measure. So this Xn, Yn is just a coupling between these two measures, and it is bounded from above the total variation distance. Okay, then let us check what's the probability that Xn is distinct from Yn. From our reconstruction, we can see that if n happens before tau, after tau, then these two Markov chains stay forever after time tau. So Xn is distinct from Yn, is bounded by the probability that tau happens after n. Because we know that after tau, the two processes will stay together forever. So this is bounded by the probability that tau is greater than n. And then let us check what is this probability. So for this transition matrix Q, this is a Markov chain, and the transition matrix is Q. So we're now just writing up So now it's just writing up what happens to the starting state. So it's a linear combination of what happens to the starting state. And this notation means the Markov chain x and yn starts from x and y, and jumping according to Q. And we want to calculate what's the probability that tau is greater than n. For this part, since we know that Q is recurrent, we know that no matter where we start from, the heating time of a fixed vertex will be finite almost surely. So the probability that the heating time is greater than n will go to 0 as n goes to infinity. So this is true for each vertex y. And now we are summing over all possible y, and we also multiply a summable sequence pi y in front. So that each of them goes to 0, will imply the whole term goes to 0. And this shows that the total variation distance between these two will go to 0 as n goes to infinity.
I don't really understand why tau is
Tau is the first time that this Markov chain hits some fixed vertex.
Oh, okay.
It's just some. So now suppose this is a new Markov chain. So tau is the first time that it hits some vertex. So it's just a heating time. Okay, so this completes the proof of convergence theorem, and this closed our lectures for the first part. And for the remaining part of the time, you will have longer exercise session. And so if you have any questions according to the discrete time Markov chain, it is better that you finish answer all of them by this week, because next week we will start a new topic on discrete time martingale. Okay, I stop here for today.